vertical circular motion and apparent weight. Vertical circular motion occurs whenever an object travels in a vertical path. Vertical means up and down along the y-axis. The other way you can think about it is vertical circular motion is whenever gravity is involved in the object's motion. So the object is either moving with or against the force of gravity. When an object undergoes vertical circular motion, it experiences a change in its apparent weight, or its g-force. Now, recall from back in the forces unit, we learned that apparent weight is equivalent to the normal force acting on an object. So, as a result of the vertical circular motion, there is a change in normal force pushing on the object. Because of the change in apparent weight, we have an increased or a decreased g-force, which can have some physical effects on the body if it's a person undergoing vertical circular motion. We're going to look at three different situations for vertical circular motion. The first is a car moving over the top of a hill. The second situation is a car moving over the bottom of a hill or through the bottom of a roller coaster loop. And the third situation we'll look at is a roller coaster car moving over the top of a vertical roller coaster loop. No matter what situation we're looking at, it's very important to remember this note. The direction of the radius for the object in circular motion is always towards the center of the circle. The radius is a vector. It can either be pointing up or down, which means the radius can either be positive or negative. You know the direction for the radius by pointing the radius towards the center of the circular motion. So for an object at the top of the hill, the radius is down, which means it's negative. For an object at the bottom or the top of a loop, the radius is also down, and the radius of the bottom of a hill is up or positive. In each case, the circular motion is caused by a net force acting on the object. Circular motion is a cause, not an effect. It's the net force on an object that causes it to move with centripetal acceleration. The net force in vertical circular motion is the vector sum of all vertical forces pushing on the object. For objects that are moving on a track or on a road, the vertical forces are the force of gravity, which is always down, and the normal force, which may be up or down depending on the situation, but always comes out of the surface. Surfaces always push against objects, they never pull. So the F net on an object in a vertical circle is the normal force plus the force of gravity. It's important to remember Newton's first law when thinking of this net force. Newton's first law tells us that an object will travel in a straight line at a constant velocity unless acted on by a net force. The net force in this case causes circular motion. and the circular motion is caused by Fn plus Fg. Fnet is Fn plus Fg, where Fg is m times little g, the force of gravity. It's important to remember that in this situation, g is negative 9.81, negative because the 9.81 meters per second is down. Fn is the apparent weight on the object. It's the weight that it thinks it has, instead of the weight that it experiences as the force of gravity. And Fnet is mass times acceleration, but in this case, the acceleration is the centripetal acceleration, or v squared over r. So Fnet is mv squared over r, the centripetal force. In most vertical circular motion problems, it's not the net force we'll be looking for. We'll usually have the speed of the object and the radius, so we'll be able to solve for the net force easily. In most vertical circular motion problems, the goal will be to determine the resulting apparent weight of the object. Because, as I said before, when a person experiences a change in their apparent weight, it can have some physical effects. So we rearrange for the normal force. Normal force is Fnet minus Fg, where Fnet is mv squared over r, and Fg is mg. We're going to use this formula in all the examples that are to come throughout this video. It's important to remember that gravity is always down, which means g is negative 9.81, and the radius can be positive or negative, depending on the situation. Depends on the direction, and the direction of r is always pointing towards the center of the circular motion. Let's look at our first example. We're going to look at the first situation where an object is traveling over the top of a hill. Example 1. A 1,200 kilogram car travels over a hill with a radius of 300 meters at a velocity of 25 meters per second. What is the apparent weight of the car? So we have a hill, and a car is traveling just over the top, and the radius of the circular peak of the hill is 300 meters. Since the center of the hill is down from the top of the hill, the r is negative. It's negative 300 meters. We calculate the apparent weight using the formula we developed earlier in these notes. Fn equals mv squared over r minus mg, which is 1,200 times 25 squared divided by negative 300 minus mass times gravity, 1,200 times negative 9.81. This gives us an Fn equal to 9,272 newtons. We can calculate the g-force on the object by dividing the normal force by the regular force of gravity, which is 9,272 divided by the force of gravity, which is m times g. I'm going to put a positive in for 9.81 because I'm just worried about the absolute value. I'm just worried about the ratio. This is 0.79, which tells us we have a reduced apparent weight. Anything less than 1 means the apparent weight is reduced and the person feels lighter than they normally do. Let's change up the speed of the car in the same hill. A 1,200 kilogram car travels over a hill with a radius of 300 meters at a velocity of 60 meters per second this time. What is the apparent weight of the car? The radius hasn't changed. It's still down towards the center of the circle at negative 300 meters, but now we're traveling faster. Fn is mv squared over r minus mg, so Fn is 1200 times 60 squared divided by negative 300 minus 1200 times negative 9.81. This gives us a normal force equal to negative 2,628 newtons. This negative is not good. You can't have a negative normal force. Fn can't be negative. When you think about it, a surface can only push against an object. It can't pull it back in. Remember this. The ground can only push. It can't suck objects into it. So that means that in this case, since the ground is below the object, the normal force can only be up or positive. We can't have a negative normal force. So what does the negative normal force mean here? What this means is that 2,628 newtons of force is required to keep the car on the hill. Since we don't have that amount of force, as a result, the car flies off the hill. It doesn't stay on the ground. The car is traveling too fast for the curvature of the hill. It flies off. So if we have our car just coming over the peak of the hill now, at 60 meters per second, it keeps on going and it flies off the hill. Not a safe situation. So let's calculate what the minimum safe velocity would be for a hill with a radius of 300 meters and our 1,200 kilogram car. We use our formula Fn equals mv squared over r minus mg. Now we know that Fn can be positive. Positive is okay, but negative is not okay. Negative is a bad result. It flies off the hill. So let's find out what happens when Fn equals 0. So we have 0 equals mv squared over r minus mg. Rearranging this, we get mv squared over r equals mg, and since m appears on both sides, we can cancel it out. This rearranges to give us v equals square root gr, or root negative 9.81 times negative 300. The negative times negative cancel out, so we have a positive under our square root, and we get 54 meters per second is our minimum safe velocity. At this 54 meters per second, this means that at v equals 54 meters per second, the car has no normal force. In other words, it feels weightless. It's that weightless feel as you come over the top of the hill of a roller coaster. It's that moment where it's not actually touching the ground, but it's still following the curvature of the hill. It feels like free fall. Here's another example, this time looking at the bottom of a hill. A 700 kilogram car passes over the bottom of a 250 meter radius hill at a velocity of 15 meters per second. What is the apparent weight of the car? So now we have a car coming down the bottom of a hill, so it's a different situation. Our circular radius points up towards the center of the circle. So the radius is positive 250 meters. The radius is positive at the bottom of a hill. This changes the situation entirely. Fn equals mv squared over r minus mg equals 700 times 15 squared divided by 250, that's positive, minus 700, which is the mass, times negative 9.81, which is gravity. This gives us an Fn equal to 7,497 newtons. We can calculate the g-force on our object by going Fn divided by Fg. This is 7,497 divided by mg, which is 1.1. The result is greater than 1, which means we have an increased g-force. The object feels heavier at the bottom of the hill than it normally would. In my fifth example, we're going to look at a roller coaster loop. At the top of a roller coaster loop, we have again a different situation. So a 10,000 kilogram roller coaster car travels around a 50-meter radius loop at 30 meters per second. What is the apparent weight of the car at the top of the loop? So here's our roller coaster loop. And our car is at the top of it, which means the radius points towards the center of the loop. And that means it's a negative value, it's down. So the radius is negative at the top of a roller coaster loop. But it's also important to notice the direction of other forces. In my previous two kinds of situations, normal force came out of the surface and went up. In this example, the normal force is down in the same direction as gravity because the loop pushes down on the car. Fn is down, so we should expect to get a negative answer for our Fn. In this case, a negative Fn value is a good sign. It means that the loop is pushing down on the car as expected. So let's calculate the Fn. Fn equals mv squared over r minus mg, which is 10,000 times 30 squared divided by negative 50, which is the radius, negative because it's down, minus 10,000, the mass, times negative 9.81, which is g. This gives us a value of negative 81,900 newtons. This is negative as we expect, which is a good sign. The negative normal force here is a good thing. It's okay because we expect that the track will push down on the car. If it doesn't push down, then we have a problem. We can also calculate the g-force on our loop. The g-force is equal to the normal force divided by the regular force of gravity, Fn, divided by Fg. This is the 81,900 newtons that we calculated for the normal force divided by force of gravity, which is 10,000 times 9.81. This gives us a g-force equal to 0.83. So at the top of a loop, we also experience a reduced apparent weight. So you feel lighter at the top of a loop than you normally would. What happens if Fn is positive for the top of a roller coaster loop? Here's our loop. And we know that because surfaces always push on objects, Fn has to be down coming out of the surface. Fn must be negative, since the track can only push down on the car. The track can't suck the car into it, so the only thing the normal force can do is to push out of the surface, in this case down. A positive Fn would mean that the track needs to suck the car into it. It would need to pull up on the car. To maintain the circular motion. Since this is not possible, if the Fn value is positive, the car will fall out of the loop. You might see a question like this. For a 10,000 kilogram roller coaster car on a 50-meter radius loop, what is the minimum safe velocity? So we have Fn equals mv squared over r minus mg. And we want to find out what happens when we set Fn equal to 0. If you set Fn equal to 0, you will get the minimum safe velocity, because this will be the last moment the track is able to push onto the car sufficiently to maintain the motion. So we have 0 equals mv squared over r minus mg, rearranged to be mv squared over r equals mg, and m cancels out because it appears on both sides. So v equals root gr, which is root negative 9.81 times negative 50, which is the radius of our loop. This gives us a minimum velocity of 22 meters per second. If the roller coaster car goes less than this, the car will fall out of the loop. To summarize, we have 3 situations in vertical circular motion: top of a hill, traveling through the bottom of a hill or a loop, and the top of a roller coaster loop. Fn, or the apparent weight, is different in all 3 situations. And there are some warnings that you should consider. At the top of a hill, we experience a reduced apparent weight. There can even be a feeling of weightlessness. At the bottom of a hill, you find an increased g-force, an increased apparent weight. And at the top of the loop, it's reduced again. It feels lighter. For the top of the hill, if Fn is negative, the car will fly off the hill. In other words, don't go too fast. There's a maximum velocity, and don't go over that maximum velocity or you'll fly off the hill. If you go too fast at the bottom of the hill, or if the radius of the circle is too small, it means that you will have too much g-force, and for the human body, too much g-force can result in passing out, or it can even result in death. It's not a safe situation. At the top of the loop, if Fn is positive, you will fall out of the loop. There is a minimum safe velocity. If you go too slow, you'll fall out of the loop.